Here at WADA Civil Works, we have taken up a request from a client to build a portal frame structure. The client's specifications for this structure include both a length and width of 28 metres, with an eave height of 7 metres and a roof pitch of 6 degrees. The rafters must be able to support an 8 kN per metre load, and the whole structure to be equipped with at least 10 windows and 2 doors, one being a roller door along with a 400mm thick concrete slab that overhangs the walls by 200mm, providing a solid foundation for the structure. Per the client's request, we have also incorporated a mezzanine inside the portal frame structure at a height of 4 metres above ground level. We extended the mezzanine across the whole portal frame with a span of 28 by 12 metres.
The mezzanine is accessible by a staircase with hand railing for safety regulations. Using a structural catalogue table, we selected the following universal beams as our columns and rafters for the portal frame. A total of 5 portal frames were implemented into the design, which is spaced evenly at 5,600mm. Girts and purlins utilised Z10010, which were chosen due to their ability to withstand inwards and outwards forces of 2.4 kN per metre. Other design points included the windows, which were placed along the external walls in between portal frames and were sized at 1,500mm by 1,200mm to provide natural light and ventilation inside the structure.
2 additional innovative components have been added to the structure to improve its sustainability. 10 skylights and 3 water tanks were added to reduce need for artificial lighting, along with the capability to utilise rainwater. The initial Revit design was then transferred into Spacegass, utilising the same design parameters to investigate its performance and viability under different loads. The design is located within the Illawarra region, thus the A2 wind region, as shown, was considered within the Spacegass analysis. This was used to extract primary loads that the design is subjected to, which consisted of the dead load, live load, internal crosswind, external crosswind, and internal longitudinal crosswind. These primary loads were used to create load combinations for the serviceability limit state and strength limit states, which the design was tested under. Linear static analysis and buckling analysis was then conducted through Spacegass, considering all loads to determine its effectiveness and check its compliance with Australian standards.
During analysis, multiple areas of improvement for the design were identified, which resulted in alterations for a more effective structure that satisfies Australian standards. The rafters were determined to be significantly stronger than required, so they were reduced in size to save costs. The columns needed to be strengthened, which increased the costs, but implementing the new beam sizes, the structure successfully met Australian design standards within the given design parameters. Additional design parameters were also met, including all steel needing to be grade 300 and all concrete used having a compressive strength of 50 megapascals. Within Spacegass, steel connections were designed for the apex connection, rafter to column connection, and the column to base connection. All connections were modified to have a utility ratio between 0.96 and 0.99 at all points within the structure, which provides effective implementation of all connections. These changes and modifications in the beams and connections resulted in the design successfully passing all design checks and all sections having a load factor greater than 1, fulfilling Australian Standards 4100 requirements.